response variable is not the response variable is not continuous, but the response variable is a rate or proportion or percentage. Okay, there's a difference between when you have, and when you talk about rates, when you talk about percentage, when you talk about fraction, that is expected to be between 0 and 1. This is not categorical, category 0 or 1, but this is like we have a range. Okay, so regard, and let me tell you this. Uh, if I want to model something in a range of 0 to 1, I need a more flexible model based on statistical theory. Beta distribution is flexible because we have two shape parameters. Okay, what determine the flexibility of a distribution is the number of shapes parameter. Okay, the numbers of shape parameter that we have. Okay, and that is why you see this. You can see the flexibility now. Okay, you can see you're having different kind of shapes. Look at that. At different values of mean, at different values of that. Now, let's look at the distribution, statistical theory. What is the distribution of the response? This is beta. Can you see that? This is what we call beta distribution with parameter P and Q. The P and Q here, they are the shape parameter. They are the one that make the distribution to be more flexible. Because if I want to model a response variable in the range of 0 to 1, then that distribution needs to be more flexible. And what determines the flexibility is the P and Q here, which are the parameters. Now, and you can see Y, which is the response variable, must lie between 0 and 1. Okay? Now, this particular distribution has been reparameterized, by Ferrari and Co. 2004, and you know what they did. Because if I have a beta distribution like this, the expected value of Y in a beta distribution is P over P plus Q. Now, if we let phi to be P plus Q, now the mu and the phi, they are the special parameters that we are actually looking for. Because let me tell you this, whenever the response variable is from 0 to 1, there's going to be we're actually going to have problem with heteroscedasticity. And because of that, and that is why we need this reparameterization, so that we can have the distribution to be in form of a mean and variance. Because this is what we want to do. We actually want to relate. This model already assumes that there's a problem, and is now, if there's a problem of heteroscedasticity, we want to make the model to reflect the problem. This is what happened. Uh, if 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 this is a model and this is data, okay, if the data is skewed, then I will make the model to be skewed. What we normally want to do is we want an agreement between the model and the data. So if you take a look at here, if you take a look at this, please pay attention. You may need this for advance. If you look at this, we actually come from here. How? We're using the fact that mu equal to that and phi equal to that. Mu is the mean. Maybe I want to talk about the mean yield. Mean yield of something. Let me take it to petroleum engineering, where we actually want to measure the fraction of crude oil that get converted to usable gasoline. United States is one of the leading producer of oil and gas in the whole world. So what if a refinery in the United States, maybe the one in Texas, actually want to know what is the percentage of gasoline, of crude oil converted to gasoline? It is not all crude oil that get converted to gasoline, because conversion from crude oil to gasoline depends on so many factors. It depends on catalyst. Has anybody read about catalyst in chemistry? The speed of the rate of the reaction. It depends on the quality of the crude oil. There are different kind of crude oil. And so on like that. There's so many. But you know what? This particular model here now want to say, okay, instead of us to have it in form of a parameter, the shape parameter, we want to have it in form of mean and variance. We actually, if I'm looking into factors that determine conversion of crude oil to gasoline, okay, then if I have some predator, then I'm going to look at the effects of the predator on the mean yield, and at the same time, I'm also going to put into consideration the effect of the predator on the variability of the yield. Not only the mean yield, we also want to put into consideration the variability of the yield. I'm quickly going to move. This is from conventional statistics, the mean and the variance of the distribution. Okay, this is when I want to model. Okay, I want to go into the regression. This is where I'm relating the link function to what? To the linear combination. Okay, so take a look at that. There's a lot of theoretical. Now, this is the variance of yi. If you take a look at this, what is happening? I'm relating variance to the mean because the model provided us, a smooth relationship between variance and the mean. Even though we know in the conventional linear regression, variance shouldn't depend on the mean, constant variance. But here, the model acknowledge the fact that there's a violation of heteroscedasticity. They want the model to reflect that. And that is why you see variance of y depending on the mean. Okay. Now, this is if I want to estimate the parameter. But you know what? I'll quickly go into this. Take a look at the two equations. One, the first equation 3 is talking about relating predator to the mean yield. But the fourth one is saying relating predator to the variance of the yield. There are two things. Equation 3, relating predator, the linear combination of predator to the mean yield. The fourth equation is saying relating the predator to the variance of the yield. Now let's go into let's look at an example here. The variable of interest is yield or proportion. In economics, you can use a beta regression if you want to know what is the amount, the amount of income that you spend on food. Of course, you are not going to spend everything on food, which is going to be a fraction, which is going to be a percentage. Now, I've given this example, the gasoline. How do we do this in R? Please pay attention. You need to load a package called beta reg. Okay. Now, here, you know what I'm doing? If you load the package called beta reg, you're going to have access to this data in R, gasoline data in R. But you know what I'm doing here? Pay attention. Look at here. Look at that. You actually going to write beta reg. In the linear regression, you normally write LM. In the generalized linear model, you normally write GLM and you indicate the family. But in the case of a beta regression, you write beta reg. Now here, the yield. What are the predator? Batch. You produce that stuff in batches. You want to look at the effect of batch. You also want to look at the effect of temperature. Because let me tell you this: in a gasoline conversion, there's so many factors I mentioned the other time: catalyst, temperature and pressure adjustment, how you maintain your refinery, and so on like that. But right now, they only want to look at the effects of the batch and the temperature. So let's look at the result. This is the result. But you know what? Look at that. That's a Z, right? Because beta regression is a member of a generalized linear model. Can you see that? So if I want to know how significant is the batch, okay, I can look at the p-value. Here, why do I have nine number? Why do I have batch 1, 2, 3, 4, 5, 6, 7, 8, 9? Because batch is categorical here, okay, and there are 10 of them, and that's why you see only 9. Okay, now Now, this is the result. But let me tell you this. This is the result of beta regression. But what do I want to do here? Please pay attention. I want to consider, here, I've only considered this. I only consider, if you look at that equation 3 is trying to say, okay, I'm relating predator to the mean response of the yield, believing that the model has addressed heteroscedasticity. But let me tell you this. If you only use equation 3, right, the model may not properly address heteroscedasticity. And therefore, also you need a expansion model in addition. The expansion model is model 4. So right now, here, this code that gives this result, I'm only considering the mean yield only. I'm not considering the variability. I'm not considering the relationship between the predator and the variability. But if I want to do that, take a look at this. Please pay attention. This is the code the other time. How many predator do we have? Batch and temperature. So if I have a belief that temperature may be affecting the variability of the yield, I'm going to write it this way. Do you remember what we did on the mixed model, variance model, the mixed model? So here, I'm actually using temperature as a dispersion variable to see whether if I use one of the predator as a dispersion variable, that will further address heteroscedasticity. And look at results. You need to look at the p-value. When that returns a significant p-value, then it means temperature, temperature here contribute to the mean yield. At the same time, temperature contributes to the variability yield, to the variance yield. Because of the fact that it is what? It is significant. Does that make sense? Now, you can decide to try that of Bash too. Okay. Now, take a look at this. If I want to go by way of likelihood ratio test, I have the first model here. This model is when I only consider the mean yield. And the second one, when I consider temperature to be a dispersion variable. If I want to know which of the two model is better, then I will do what I always do before. Do you remember that? That we normally say ANOVA, but here we're not going to say ANOVA. We're going to say LRO test the first model against the second model. And what do you see here? You look at the p-value. You know what the p-value is trying to say? The p-value here is less than 0.05. Let me tell you this. Under the null hypothesis is saying I do not need a dispersion variable. But on the alternative is saying I need a dispersion variable. Now that the p-value is significant, then I'm actually going to say using temperature as not only contributing to mean effect, but also contributing to the variability. So you are trying to say temperature is the reason why there was heteroscedasticity in the first place. Does that make sense? Okay. Now, that's another example. Now, I quickly, this is another example, when you want to talk about the percentage of income that you spend on food. It's a function of what? The income itself and the number of persons in your household. That is what economists told us. If I want to know, okay, because food divided by income, the amount that I spend on food divided by the total income is going to be a rate. I'm now actually regressing that on the income and the number of persons in the house. If I use a mean model only, okay, I'm actually going to get this result for the mean model only, telling me the income and the person is significant individually. But I don't know whether this has addressed heteroscedasticity. And to better understand, I have to use one of the predator as a dispersion variable. Okay, which is, oh my God, why am I using persons? Okay, I have income, I have persons, because at times where I'm using person here, the number of person in your household may determine the amount of money you're going to spend, amount of income you're going to spend on food. And that's why I'm using person. And at the end of the day, when I actually perform the likelihood ratio test, do you see the p-value? It means persons contribute not only to the rate, to the amount of income spent on food, but also contribute to the variability. That's exactly what you see. Okay. Then you can also use AIC. Okay, the model with the lower AIC is the best model. So we should see that guy. Now, the last thing I'm going to say today, I think I'm going to spend like 2 more minutes. Okay, you can also judge by using what is it called? Now, I also want to talk about the choice of link function. I told you the other time. When you change the link function, you change the functional relationship. Now, instead of me to use uh just logit, and I use the complementary log. Let me tell you this. Logit, we assume in beta regression here, we assume that your proportion rate is very close to 1 or very close to 0. So it's around 0.5. But complementary log is being used when there's an extreme value of rate. Like in a fractional distillation, we normally want to have something, majority of the crude oil is being converted to gasoline. So situation where your rate is very close to 1, that's an extreme. We normally go with the complementary log. So here, I'm trying to look at the effect of the link function. The complementary log, you can see the R square is very high. Okay. And if you take a look at this, take a look at this guy. I have 3 modules. I want to see which one is the best. The first module here is when I use log reading, and when I use the logit, I did not use any variable as a predator, as a dispersion variable. The second one, I use a logit, but I use temperature as a dispersion variable. The third one, I use a complementary log, but I did not use any dispersion. I want to see this one is the best. I can look at the AIC of all of that. The one with the smallest AIC is the best. Okay, so take a look at that. So, link function that you select at times, we also impart, what the efficiency of your model. This is where I'm actually going to stop. And our meeting on Wednesday is online. And that very meeting is actually, I'm going to give you information about the final exam. I'm advising, I'm encouraging every one of you to attend because there's going to be a lot of information that I'm actually going to dish out. We've started strongly. I want us to end strongly. That's all what I got. Stay safe, stay warm. But for now, everyone.